Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, of course, we did talk about how we can, let's say, if you have a resistor or pure resistance, let's say, an inductance and a capacitors, all these were connected in series. How, of course, you're going to find the effective voltage, you're going to find the, let's say, the total effective voltage, let's say, and you're going to find the current, and then, of course, the impedance or the total impedance of the circuit as well. And, of course, we followed, let's say, following that, we've solved some questions. And of course, we ended up right here. Question 54. Now, at this question here, what does it say? It says, given an AC source of an instantaneous potential difference here. So it is very important to know that whenever, let's say, an instantaneous values of voltage or current were given, you can always extract the maximum values of, let's say, from this equation, and of course, omega most of the time as well. So these are most of the time will be given to you. So don't forget, this part is maximum. So we have potential difference. So this is going to be V maximum and this is going to be omega here. So, and of course, what do we have in this circuit? It says we have a pure resistance of 20 ohm, don't forget. And also says a coil of self-inductance, that is L, which is 3/5 pi Henry, and a negligible resistance. So we have a resistance in the circuit, but this resistance is negligible. And of course, a capacitive capacitance 1/4500 pi. That is in farad. All, or you can say, are all connected in series across the source. So calculate the following. So of course, we have the first thing to calculate says the inductive impedance, that is XL of the coil, the capacitive impedance, that is XC of the coil, and the total impedance, that is Z of the circuit here. So we're going to do this one here, says, and then part B, find the effective current of the circuit as well. But before that, let us draw the circuit, okay? So here's the circuit that we have. These are, so we have an alternating current, that is the source in here. We have, let's say, we have an inductor here, or self-inductance, you can say. Negligible, let's say, resistance here. So I'll draw this one here. And of course, we have a pure resistance here. And also we have a capacitor that is also connected in the circuit here. But it says of negligible, resistance here. So we can take this part out of the circuit. So this is L, and of course the value is given. As you can see here, the value is basically 3/5 pi. And of course, we have this pure resistance, which is 20 ohm. That is the value for this, that is R. And of course, we have this value for the capacitor, which is 1/4500 farad here. Okay, so these are the values that we have. And of course, this is fine. XL, XC, Z, and of course, I effective of the current as well. So let's solve this one together. Okay. All right, let's keep this one here. Okay, let's keep this part too. All right, so what do we have first? Remember, these are the values that we have. So the first thing to find says the inductive impedance, XL, yeah? Can I find XL? What is XL equal to? Let's change this one too. Okay, yeah. So XL, we've learned that XL equal to omega L. If not, you could just directly go with 2 pi F times L here. And of course, this one here, 2 pi times the frequency of the circuit. What was the frequency of the circuit? My bad. We don't have to do this one since we have this one here. It says, let me go back to and write this one here. Okay, no, this one. So we have V instantaneous here, so we don't have to write actually the frequency of the circuit since omega is given, so you don't have to worry about that one. That is 100 times the square root of 2, and of course 100 pi omega t here. So let's go back to this and write this in the circuit here. So this is V instantaneous, we can say. That is, okay, I feel like I forgot what it was. Okay, that is 100, yeah, 100, of course, with 100 again. Okay, so 100 square root of 2, that is sine 100 pi t here. So you can see this is omega, and this is, of course, you can say V maximum here, 100 pi, not the sine with the sine, yeah, without the sine, don't forget. So we can, where's this one a little bit? Okay, so this is what we have. So now, as you can tell here, since I have omega, I really don't have to say 2 pi F. So we can erase this one here. Okay. So what is omega? Omega, obviously, it is 100 pi multiplied by L. What is the value for L? It is 3 over 5 pi, yes? 3 over times 3 over 5 pi, and of course Henry. So of course you do the math here. That is, you can say 20, this is 1, so this pi or the 2 will cancel out. It is obviously going to be 60 ohms. Here 60 ohms, okay? That is XL here. Okay, what about the second one? So the second one says find XC here. What is XC is equal to? 1 over omega C here. So 1 over omega, again, it is 100 pi multiplied by, what is the value for C here? The value for C, as you can see, it is 1 over 4,600, yeah? Okay, 4,500 actually. Is this 5? Okay, 4,500. 4,000? Let's write, make it a bit more clear. 4,500, and that is pi, obviously. Oh, no, my bad. It is 1 over that, 1 over that. So don't do the same thing here. So times 1 over 4,500. Well, my 5s look like 6 now. I don't know what is wrong. 4 times 5. 1 over 4,500 pi here. And of course, you do the math, you will find the answer. What is XC? So let's get a calculator back. All right, so that is what we have. Now these two zeros cancel out. We can say pi and pi cancel out. This 2 will cancel out with this one. So this 45 goes up, so we can say 45. 45 ohms, yeah? Okay, let's double check with this. 100 pi multiplied by, we have 1 over 4,500, and that is pi. Oops. Okay, so the answer is 45. It is correct. Okay, that is the second one. That is XC, you can say, yeah? Inductive impedance of the capacitor. And the total impedance of the circuit here. So how do you find the total impedance of the circuit here? But so in order to find the total impedance, that is Z obviously, we've learned that equals to R squared plus XL minus XC, the whole thing squared, yeah? So we do have the resistance of the resistor, let's say. The resistance of the resistor is 20, so we'll say 20 squared plus XL, we found, which is 60, minus 45, correct? And then the whole thing squared. And obviously you can see that XL is bigger than XC, of course, so this circuit would have an inductive property. In another word, the voltage would lead the current here. Okay, so we'll go with this. We'll say 20 squared, right, plus open bracket, that is basically 60 minus 45, that is 15 obviously, and then the whole thing squared. So the answer is going to be 25. So the total impedance of the circuit is 25 ohms here. Okay, so this is we can say the requirement for the first part of this of the question. The second part says find the effective current of the circuit. Now finding the effective current, it is easy now, yeah, because we have the total resistance, which we call the, not the resistance, let's just call the impedance, and of course we have, but by the way, this value that is given is obviously V maximum here, so we cannot use that one. So how do I find, okay, so it says the effective current. Normally, we'll say V effective total, obviously, equals to I effective, that is the total again, and then multiplied by the impedance, that is, you can say, the resistance of the whole circuit here. So we want the effective current. So effective current equals to V effective total, okay? And then, or the source, for the source, divided by this. But remember this, don't you go and try this one here, because this is not the V effective. This is V maximum. So how do you convert this one to V effective? We've learned that V effective equals to V maximum over the square root of 2 in here. So we have V effective, that is 100 square root of 2 divided by this 2. So these two cancel out. So of course V effective, it is going to be 100. So let's write it down, yeah? So V effective is 100 volts here. So we'll say 100 volt divided by, and the total, the impedance was 25 there. So it is actually look like that. Okay, so 25, then of course 100 divided by 25, that is going to be 4 what? 4 amperes. So we can say I effective through the circuit is 4 amperes here. So this is how you can find the values. But remember this, always follow, let's say, what is required step by step. So try to find, let's say, the parts that are known or the parts that you know, then try to see, for example, what are the equations used to find this unknown, and then see if you have everything that is needed in the equation. If not, let's say, if that is the only equation, obviously you need to use it. If there are other equations, if you have unknowns, let's say more than one unknowns, then try to see if there are other equations you can use. If not, then try to find these unknowns so that you can find the one that you're seeking to find, let's say. So that is basically the current we found, and of course, everything else that we have. Okay, now we have another question here, which these questions pretty much, like very close to one another. The idea are very similar, you can say, with a bit of course, some of them has a bit more, some others have a bit less than that. Okay, now take a look at this one. This is a bit interesting. It says a capacitive capacitance, so we have the value for C, which is 400 microfarad, is connected in series to a pure resistance. Okay, so to a pure resistance of 10 ohm, and of course an AC source of frequency this much. The effective value for the potential difference across the capacitor is 18 volt in here. Okay. Okay. Obviously I should have. Okay. Now take a look here. In the let's say the new version of this, I've provided some drawings by the way. It makes it very easy to tell how you can solve this one, but clearly it's not the one that we're using actually. Okay, so that is something I should have used from the beginning. But anyway, I'll draw the diagram for you so that you know how it is. So we have a capacitive capacitance this much connected in series with a pure resistance. So we have a circuit. This, of course, alternating circuit. And of course, we have the value for capacitance here. And of course, we have a pure resistance here. Okay, the value for this capacitance, as you can see here, or the value for this resistance, it is 10 ohms. And the value for this capacitance, you can say, okay, where's this one? It says 400 microfarad. So C equal to 400 microfarad. And the frequency of this source is, or before that, let's say, the voltage across this, the voltage across the capacitance here, where the capacitor is 18 volts. So we can say VC, okay, this voltage that is obviously VC, it is 18 volt in here. And the frequency of the source is 250 over pi hertz. Okay, so what are the requirements first? It says find the effective potential difference across the pure resistors. Okay, so effective potential difference across the pure resistance. So we have the let's say the effective value of okay, what is it? Just double checking with this. So we have this. It says okay. It says the value potential difference and the effective value of the potential difference. That is the, you can say effective over this is this. So find, let's say, the VR here, or the potential difference across the pure resistance. So ask yourself, how can I do this one here? Well, first of all, in order to know this one, we do have the value for, let's say, the resistor. What I need to do is, first of all, if I could have the current with the resistance, then obviously I would have been able to find VR here. So let's write the Ohm's law here. We can say VR equals to I times what? Times R in here. I have this one here, okay? In order to find VR, I need the current here. And of course, the current in the circuit, since it is series circuit, the same everywhere. So, but how can I find the current here? If you can tell here, I have the voltage over this, and I have the capacitance, or the value for the capacitor here. So if I could find XC here, and using XC and VC, I can find the effective, or the current, let's say, the effective current through the capacitor. And if I do that, then of course, I'll be able to use this one right here. So I will say, we do know that VC here equals to what? Equals to IXC here. Okay, so if I find the current here is the same current there because it is series circuit. So we'll say I effective here equals to V over the capacitor over XC here. But the question is, do I have XC? The answer is no. Can I find XC? Yes. So what is XC is equal to? XC is equal to 1 over omega C here. Do we have the value for omega? No, but we have the frequency. So it is equal to, let's use a different color. It is equal to 2 pi F, and F, the value for F is 250 over pi, and then multiplied by the value for C, value for the capacitance, which is 400 micra. Micro is 10 to the power negative 6. So you do the math, you can cancel out this 2 times 250, that is 500 times 400 times 10 to the power negative 6. That is all, you can say under 1, okay? So let's find the value for XC. That is 1 divided by 2 times, that is 500, we can say, multiplied by 400, and then multiplied by 10 to the power negative 6. And of course, the answer is going to be 5 ohms here. So XC, why am I writing X sub 5? That's strange. So equals to 5. But 5 what? 5 ohm, because that is an opposition, or you can call it a resistance here. If I have XC, now of course I can plug it into here. So we'll say VC, which is the voltage over the resistance, let's say over the capacitance, that is 18 volt, divided by XC, which we have just found, that is 5, yeah? So of course I can find the current here. So we'll say 18 divided by 5, the answer will be 3.6. So the current through the circuit, we can say it is 3.6 amperes. Don't forget this. Now, of course, I can use this value right here to find the voltage over the pure resistance. So VR again equals to the current, that is 3.6 multiplied by the resistance of the resistor, which is 10. So of course we can say 36 volts. Okay, that's a bit high, but this is what it is. Yeah, so 3.6 times 10 to the power 3.6 times 10, it obviously equals to 36 volts. Okay, now that is the first part of the question. The second part says find the maximum value of the potential difference of the source. Find the maximum value of the potential difference of the source. So how do you find the maximum value of the potential difference? Now, in order to find, I think we should erase a few parts, but maybe afterwards. That was all part A here. So for part B, remember, it says find the V maximum. So first of all, we're going to find V effective total, and then after that, of course, using the total or the effective, we'll find V maximum here. So find V effective total equals to, we can say VR squared plus, of course, VC squared, okay? So because we have two voltages there, so VR, that is 36 squared plus, and then 18 squared. So you do the math. Let's see, what will it be? That is 36 squared plus 18 squared, and then the answer will be 40.2, we can say. So V effective total equals to 40.2 volt, or you could just say 40, that would also be correct. But remember this is only the V effective. What does the question want? It wants V maximum here. So in order to find V maximum, of course, you will use, let's say, V maximum equals to V effective. Oh, what did I do? Okay, so now this is V effective, yeah? V effective total. To find V maximum here equals to V effective, obviously, multiplied by the square root of 2 in here. So now we have 40.2 multiplied by the square root of 2. That, of course, will give us the V maximum of the source of the voltage or alternating current here. So 40, we can just, by the way, we can just leave it this way right here. Once again, it depends on, like, for example, how they'll bring this question. If it was left with, or you can see if there is a square root, you can keep it like this. If not, you could just do the math in this case here. So 40.2 multiplied by the square root of 2. Then, of course, the answer, that was incorrect, 40.2 times the square root of, that's, keep doing 3 instead. Okay, 40.2 times the square root of 2 in this case. Of course, the answer we will get, it would be 56.8, which is, we can say about 57, yeah? If not, you could just keep it this way, 56. As a matter of fact, we can round it like to 56.9 instead. You can also sometimes write 57 volt as well. These are in volt. So see what we've done, yeah? Remember, we wanted to find the first part, we wanted to find the voltage over the resistor using this voltage, and of course the value for the capacitance using XC. We found the current. Using the current with, let's say, the resistance, I found the voltage here. The next thing, it says find the V total, or let's say the maximum of the circuit. So first of all, we'll have to find V effective, which equals to VR squared and the square root, of course, plus the VC squared. Doing that, of course, we get the V effective total here, but then we don't want V effective total, we want V max. So using the equation, let's say V effective equals to V max over the square root of 2, using that equation, you can find V maximum, but of course, by using cross multiplication, and then you will find the answer. Now, the last requirement here says what? Represent vectorically the potential difference across the resistor, across the capacitor, and of course the source as well. So now we're going to draw all this, by the way, as we have saw before that, and of course we said that, you can see here, where was it here? We can see that this is basically VR and this is VC and all that. So we found this one. So how are we going to do this one or represent this one using vector diagrams here? Now we do know that over, or you can say across the resistor here, the voltage and the current, of course, they are in phase. No one leads or lags, let's say, behind the other one here. So they are in phase. But when it comes to the capacitor here, we do know that, let's say, on a capacitor here, we do know that the voltage lags the current leads here. So if we're going to represent or draw the vector diagram for this one, this is going to be for both, let's say, VR, and of course this is IR as well, because the current is the same everywhere. So of course you could just say I instead of the R here, but that is the case here. And then because we have a capacitor here, in the capacitor we do know that, let's say, the VC would be lagging behind the current. So if this is VC and this is the total current there, okay, we do know that the voltage lags behind this one. But of course, if we're going to use this one here, we can put a negative value because it is negative for the angle. This one is lagging. So using the vector diagram here, of course, we'll have to translate this one to this. So this is, we can say VR, and then of course this is VC or negative VC. And then if you want to find the total, of course, you'll have to use Pythagorean theorem for that. And of course, it is going to be this much here. So we can say this is V total here, okay? That is V total for, let's say, the entire circuit, and obviously is going to be, you can see that it is clearly the voltage lags behind the current by some degrees here. But that is basically the representation for or vectorically for when we have a pure capacitance and of course a pure resistance connected with a capacitor here. So that is how it is done. Okay, moving forward. Now let's talk about a new concept, which is basically this time, so far we've been talking about a resistor, an inductance, let's say, and or we can say a coil, and of course a capacitance. All these are connected in series, but now we're going to talk about these being connected in parallel. Will it be the same? Will it be different? What are the similarities and what are the differences that we can have? Now, so far in grade 11, of course, you've learned the difference between series circuit and parallel circuit. In a series circuit, all the components are connected one after another, or you can say there is one loop throughout the circuit here. But in parallel circuit, of course, we have, let's say, at least, let's say, 2 loops, or if not more, let's say. Okay, so we can say the minimum loop would be 2. Of course, we'll say there is, to make it simpler, we'll just say there is more than one loop in the circuit. But there are other differences between the two as well. We do know that, let's say, the current in series circuit is the same, but in parallel circuit, the voltage is the same because you can see we have different loops. So we'll have, let's say, the same voltage across every loop here. But we also have mentioned that in series circuit, the voltage were additive, but now in parallel circuit, the current will be additive. And of course, this current being additive changes the equations a lot, or you can say what we're going to do in terms of finding the voltage, in terms of finding the current, of course, will change slightly, or if not a lot, yeah? So what are the differences? Let's talk about this. So first of all, we have a circuit, you can see. Okay, I'll reconstruct the circuit one more time. So here's the, let's say, first of all, we have an alternating voltage or circuit, you can say, source to be more precise. And of course, let's say we have, let's say, a self-inductance here. And of course, we have, let's say, we can say a pure resistance here. And of course, we have a capacitor that is connected as well here. So you can see This is L, this is R, and of course this is C here, and this is the alternating circuit with, you know, like a certain frequency as well. Now this is a parallel circuit. Remember, in parallel circuit, all the voltage is the same, so we can say V total is the same as the voltage across the, let's say the L. Let's start with the L first. Okay, it is the same as the voltage over L, which is the same as the voltage over R, which is the same as the voltage across the capacitance as well. But in terms of the current will be different. So how do we find the current here? Of course, the current over, let's say, the inductance is going to be using Ohm's law, by the way. So we have Ohm's law says V equal to I times R, let's say, or you can say R equals to, let's say, V over the current, yeah? But we want the current, so let's just go with the current here. So in order to find current, we'll say current equals to voltage over the resistance here. That is for the pure resistance, let's say. We can have the same thing with this. So we'll say the current across, or let's say not across, that is passing through the inductance here, we can say equal to V over, that is the same if you say V total or VL or VR or VC. So we'll just go ahead and write V. But by the way, once again, if we're going to use V effective, all the other values are effective. If you're going to use V max, which unlikely, but still correct, we can use V max over, let's say, R, you can say, not R here. If we have, then this current obviously becomes the maximum as well. Okay, but the point is, we have V effective, and of course is going to be over XL here. That is for, let's say, the current through the inductance here. What about the current through the resistance here? We can say IR, it is obviously equal to V effective, which is the same as, you know, like everywhere through the circuit, equals to, not everywhere, on a parallel circuit, okay? And then equals to, or let's say divided by R. And of course we have IC, that is VE or effective over XC here. But don't forget, okay, because the current, or these currents are additive, by the way. So how are we going to do this one here? So in order to find the total current here, we'll say, okay, the square root of, just like, for example, what we have used before. So we will say IR, that is squared, okay, plus we can say, but there is a little bit different here, you can say, yeah? And, okay, so not this one precisely, yeah? Okay, so let's just keep it this way for now. If we're going to add all this together, okay, so we can say this plus, now of course we will say IC this time minus IL here. And I'll tell you why IC minus IL in a second here. But this is basically, don't forget the square. And of course this is going to be in a person. This is how we can find the I total here. Okay. What about regarding the resistance here? Regarding the resistance, of course, we can say Z equals to, without proving the equation and all that, we can say 1 over the square root of 1 over R, and of course that is squared, plus we can say 1 over, let's say, XC minus 1 over XL in here. But of course, we can simplify it down a little bit further. 1 over the square root of, we can say that is Z, obviously, 1 over R squared, 1 over R, the whole thing squared, plus 1 over C, or XC is equal to 1 over omega C, yeah? So if you do, or, you know, like, for example, write this one here, of course, you can get omega C here. And then, of course, minus, we can say 1 over omega L if you want to, and then the whole thing is squared here. So you can either write this one, or you can write this one based on what is given in the equation. Now let's talk about why do we have IC, because in the previous thing, in series circuit, we had, let's say, we were dealing with voltage, of course. We used to find the total voltage, but we were saying, let's say, VL minus VC, let's say, or where we're talking about, let's say, the total impedance, where we're saying, let's say, R, and of course, plus 1 over, let's say, plus, not 1 over, plus, XL minus XC, or in another word, we were let's say saying XL ahead of XC first. But why is it different here? Let me tell you why. So in order to do this one, let's say, or to represent this one, let's say, vectorically, we have this. So in series circuit, or not series circuit, in parallel circuit, we said that the voltage is the same everywhere in the circuit. So if we consider the voltage and the current through the resistor, these two, obviously, we can say I across or through the resistor, and this is V over the resistor, because they were on the same, or there is no phase difference between the two, so this is what will be between the two. That is for the resistor, okay? And then remember this, for the inductance here, we said previously that whenever we have inductance, voltage leads the current by what? Leads the current by 90 degrees here. So I can say that or you can say, if that is the case, and then for the capacitor, before continuing this one, in the capacitance, of course, the current we're leading, let's say, leading by what? Leading by 90 degrees here. Okay, so if I want to do this, so because remember this, we're trying to find the total current here. So instead of or, in order to say that the current is leading for the capacitance by 90 degrees, so here's what we're going to do. So this one, of course, is going to be VC, not VC, my bad. It's going to be IC. The current, you can say, the current IC here, it is going to lead by 90 degrees positive, or you could just say pi over 2, that is positive here. Why we're doing this? Because across the capacitor, or you can say for the capacitor, or when we had a pure capacitance, we were saying that the current leading the voltage by 90, if you remember. So the current leading the voltage by 90, that means the current for the capacitor would be leading by 90 compared to the current for the resistance here. What about for the inductance here? For the inductance, of course, we were saying the current lags behind the voltage. So in another word here, the current were lagging here. So we can say this is IL in here was lagging, let's say, by 90 degrees here. So we can say this is negative 90 or negative pi over 2. This is these are positive, by the way. So it would be this. But once let's just make this one a bit smaller. So if you're trying to combine these two, what would you do here? Obviously, these two are in opposite directions, so we're going to subtract them, and then after that, these are at right angle with this one, so of course we will use Pythagorean theorem here. So if we do these two together, like if we subtract this one, we will get something like this. Okay, so if I just drew the current now, let's say this is IR, and of course we would have, let's just say the value for IC is bigger than IL. In this case, you will say IC minus IL here. And of course, this is what you get as a result. And of course, you'll move this vector right here. So let's say this is IR, and this is, let's say, IC minus IL here. So now then you will do the Pythagorean theorem, and this is, of course, is going to be I total here. So if IC were bigger than IL, of course you get a positive, let's say, angle here, or positive angle, or theta would be positive. If it is positive, that means the current is leading the voltage here, okay? Which is quite opposite to what we had before in series circuit. In series circuit, if the angle theta, in series by the way, in series circuit, if the angle were positive, that means the voltage were leading the current. But here now, if we're, let's say, parallel circuit, if the angle is positive, that means the current is leading, okay? Because remember this, we have IC minus IL, you can say. Okay, and then of course, what if the voltage, or let's say IC were smaller, then of course this would be the angle here, then you get a negative angle. Getting a negative angle here, all right, in parallel circuit, getting a negative angle, that means what? That means the current is lagging behind the voltage, okay? Or you could just say the voltage is leading the current, which is the same thing. But of course, if you do remember in series circuit, if the answer or the angle were negative, we were saying the current was leading, or the voltage was lagging behind the current. But it is quite opposite here. So if we get a negative value here, that means the current is lagging behind the voltage. And of course, that is where it comes from. This is basically vectorically, you can say. So, but the final angle, you can see that this is the total, yeah? So the final angle, or this angle is going to be between what? Between the total current and of course the voltage as well. So this would be the voltage, let's say, because that is the voltage, yeah? And then this is the angle, or you can say the total, this is the total current, and of course this would be the angle between the current and the voltage there. So remember the equations that we have? Okay, so these are, by the way, we've run through this. So for the current, we can say, whenever you want to find the total current, we'll say IR squared, and then once again, careful, IC minus IL, the whole thing squared. And then in order to find the resistance, total impedance, my bad, we can say 1 over what? 1 over R. You can say 1 over R squared, or you could just say the whole thing squared. Perhaps it would be easier in this case. Ignore this one. The same thing, by the way, yeah? Because 1 squared is still 1, so we'll just give the square to the R, but don't use that one. Just make this one squared, and then, of course, omega C minus 1 over L, omega L, the whole thing squared here. And where does this equation come from? Of course, it comes from this one right there. Okay, this is basically, we have the current, we have the voltage, since the current equals to voltage over the resistance or the total, because we're trying to find total here. And then, but remember this, yeah? Since the voltage is the same everywhere in the circuit, so we can take like voltages here as a common factor, we extract it, and the voltage here and there will cancel out. Once they do, this is the equation that is left, yeah? But this is 1 over Z, so of course you can just bring this one, or you can cross multiply, so Z equals to what? Or something before that, you could exchange this one. This is 1 over omega XC, and then XL, then of course XC equal to, now this one is equal to 1 over omega C, yeah? But then of course 1 over this, of course this one goes up. This is what you get as a result. Then we want Z here, yeah? So of course you can bring all this, or cross multiply, or just swap their places. So you bring this one right here, take Z to the other side. This is what you get as a result, and that is basically the total impedance of the circuit. One thing that I forgot to mention actually, we've mentioned the angle, okay, but how do you normally find the angle, let's say, between, let's say, the current and the voltage, whether the current is leading or the voltage is leading? That is by using this. Or you can just say, instead of saying tan theta, you could just go ahead and write, let's say, theta, a short form for that, you can say, is equal to tan inverse of, but don't forget exactly what we have there, yeah, for this one here. So we're going to say this over this one right here, because if you draw, or if we draw this one, that is IR, and then of course we had IC minus IL here, yeah? So obviously for tan theta, opposite over the adjacent here, so we get IC minus IL over IR here. So this is what you do, but be careful here. If you didn't have one of the values, let's say, if no capacitors were connected to the circuit, so this part would be out of the equation, but don't forget to keep this negative, yeah? Or if, let's say, no inductance were connected in the circuit, this part will be out of the equation here, then of course you will always use, let's say, what is left in the equation to find the total impedance, to find the current, to find the angle as well. But this is how you find the angle, but it's very important not to forget, if you get a positive value here, that means the current is leading. If you get a negative value, that means the current is lagging, which is quite opposite, or you can say exactly opposite to a series circuit. And one more thing here. What happens if these two values were equal? Remember this. We have a situation where if omega C is equal to 1 over omega L, just in case, if these two were equal, that means this part would cancel out, okay? So once again, imagine or pretend that if omega C here is equal to 1 over omega L, then this part, of course, would be equal to 0. And if that is the case, then this one would cancel out with this one here. So you can say 1 over Z equals to what? Equals to 1 over R in here. And of course, you can cross multiply, then you can say Z is equal to R in here. Or you can say, as a matter of fact, here, you can, that will be, in this case, we can say the circuit will be in a state of resonance here. But remember, that is for parallel circuit here. So what happens exactly if, let's say, the circuit is in a state of resonance here? Then you can see here, 1 over Z is equal to 1 over R. In another word, you can say the current or the resistance will be maximum. If that is the case, then of course the current will be minimum in the circuit here. Okay, so take a look here. We have a few more study tips. What does it say? It says, in parallel circuits, the potential difference are equal. Don't forget. That is because we have, let's say, a parallel circuit. The phase difference between IR and VR is always 0, because we've mentioned the voltage and the current, let's say, over or across the pure resistance is 0. There's no phase difference. But don't forget, the current over, let's say, the inductance lags behind the potential difference by 90 degrees. We've mentioned this one for series circuit. For the inductance, let's say, the voltage leads by 90, which means the current is falling behind, yeah, by 90. Or you can say that another way to say IC leads the potential difference, let's say, leads the potential difference by 90 degrees. And of course, we said for the capacitance circuit, that is still in series circuit, we've mentioned that if we have a pure circuit, a pure capacitance in the circuit, the voltage, we're lagging behind the current. Instead of saying the voltage lags behind, can we say IC leads the voltage by 90? Yes, and that is the same thing here. But don't forget, the phase difference between IL and IC, this one of them is leading by 90, the other one is lagging by 90. So what is the total phase difference between the two here? So of course it is going to be 180 here. Let me not forget or redraw this one here. So that was, let's say, IR, and of course this is IC, and this was IL here. So this is leading by 90, this is lagging by 90. So what is the phase angle difference between IC and IL? Of course is going to be 180. Okay, and then what else do we have? It says if a parallel circuit is in a state of resonance, of course the current decreases because Z increases, like we've said before, yeah? If omega C is equal to 1 over omega L, then of course that part in the equation will be 0, then the circuit will be in a state of resonance, then the current decrease. Why? Because the resistance will be maximum. But that is only true for parallel, because in series circuit, we're going to study later, is going to be opposite to this one here. So if the series circuit is in a state of resonance, the current increases because that is, remember, we're talking about series now, yeah? But if we have a series circuit in a state of resonance, the current increases because the impedance, or Z, decreases, you can say. So watch this. It says if the circuit has only resistance and capacitance, this is where we're going to write. So you can see without IL, you can see it. So IL is out of the equation here. We'll just say I equal to IR squared plus IC squared. And then for tan theta, or you could just say theta equal to tan inverse of IC over IR here. It's normally IC minus IL. IC minus IL divided by this, but if there's no inductance, you can just cross it out, so will be IC left here. But if the circuit has only resistance and inductance, that is no IC here, so of course we have this, but don't forget, now the equation is IC minus IL. If this is 0, we can say, or it doesn't exist, so 0 minus this, you'll have to keep this negative here so that you can get a negative value over there. And then the last 2 points here, we said that if the theta is positive, but remember, in series circuit before, we said if it is positive, the voltage leads the current by 90, yes? Or by this degree, not 90, my bad, by whatever the value of the theta is, okay? But if it is in parallel circuit, and if it is positive, remember, because IC is above, so that means the current leads the voltage, don't forget, okay? The current leads the voltage, but once again, if the theta is negative, if it is in series, we said the current leads, yeah? But if it is negative in parallel, that means the voltage is leading. So you can see these two are exactly opposite to one another. We have a Zhyar question, says what? In an AC source, or an AC source is connected across a parallel combination of pure resistance, so we have a parallel combination. It's very important to remember this. A parallel combination of a pure resistance, a pure self-inductance here, of course a capacitance. So we have R, we have L, you can say, and we have C. And the angle, let's say the angle of phase difference between which of the following is 180. So between which one of these is 180? Is it between R and L? Is it between R and C? Is it between L and C? And of course, because since we're talking about the current here, so is it R, let's say, is it R and C? The answer is no. Let me redraw this one for you just so that you remember this. This is, let's say, IR, and of course this is IC here, and let's say this is IL here. So whenever they talk or they ask about angles in parallel combination, you can always do this one here, okay? So you can see let's say the first one says IR and IC, that is obviously 90 degrees, so not this one, because we want 180. IC and V, okay? IC and V here, that is, this is basically where the V is, yeah? So this is, you can still say 180, oh my bad, okay, so this 90 still. What about IL and IC? IL and IC, of course, you can see that this angle between the two is 180, and of course, this is the correct answer. What about the last one here? It says IL and V, okay? So this is IL, this is IR, and of course, this is the V because the same always, so this is also 90, so incorrect. So the only correct option here is going to be option C, so not this one, okay? We just circle this one for the sake of focusing, otherwise, not as an answer. Okay, so the answer was IL and IC. All right, and of course we have one question regarding this, regarding a parallel circuit. Most of our questions, obviously, it is regarding, let's say, the series circuits combinations here. So we have, says what? It says chapter view. We have an AC. Okay, I wonder if I have enough time to solve this question. I think we'll make it. Okay, says what? What does it say? It says an AC source of frequency of 1 megahertz. So this is the frequency of the source of an effective value of 50 volt is connected across a parallel combination of resistance of this much, inductors of impedance this much, and of course a capacitance of this much. Calculate the following. Yeah. So let's do this together and see how it is done here. Okay. All right. Keep it here. Okay, not this, not this. All right, so the first thing says, find the impedance of the circuit, the total resistance of the circuit, yeah? So don't forget these are the information given. We said the impedance of the circuit equals to what? Equals to 1 over, okay, the square root of 1 over R, you can say. By the way, you can see that we have R, we have XL, and of course we have XC and all that, so we can just use this one, 1 over R squared plus, remember, we can say 1 over XC minus 1 over XL, and then the whole thing squared. If I did not have XL and XC, I would have, for example, used omega C minus 1 over omega L, let's say. But since I have this one, I can just use this one here. So let's say 1 over, okay, square root of 1 over R squared. What is the R? Not this. Okay, the R that I have, it is 300, so 1 over 300, the whole thing squared. And then plus 1 over XC. What is XC here? XC is 200. And then minus 1 over XL, which is 600. And then the whole thing squared. Now do the math and tell me what is Z, or the total impedance. Let's get the calculator back and then find this resultant here. Okay. So we have 1 over, okay, and then the square root of, we have 1 over, okay, this takes a bit of time, 1 over 300 squared, and then plus, you can open bracket, 1 over 200, and then minus 1 over 600, then close bracket, and then of course squared again, and then press equal. So the answer is going to be 212, that is 212.1, we'll just ignore the 0.1, that is going to be in ohms. This is the total impedance of the circuit here. That is the first part. Second part says the effective value of the current that passes through the resistance, the inductance, and the capacitance. So now we have the voltage of the source, yes? Do we have the voltage for the source? Because if we do, then of course we will be able to find each one of these. So, okay, it says the effective value of the current. So I here equals to V, because the voltage of the source is going to be the same everywhere in the circuit here. I mean, over each component since it is parallel. So V over R here, that is, let's say, IR. And of course, for IL equals to V over XL. And of course, for IC, it is going to be V over XC here. So these are, let's do the math here. But first, let's see what was the voltage of the source. It was 50 volt, yeah? The effective 50 volt we're going to do this one, 50 volt. Okay, so we'll say 50 volt divided by the resistance, that is 300. So 50 over 300, that is 5 over 30. The answer is equal to 0.1617 by rounding. 0.17, it is going to be amperes through this one here. And for this one, it's going to be 50 over, and then XL is going to be 600. So 50 over 600, that is obviously 50 divided by 600. The answer is going to be 0.08, we can say. 0.08, that is amperes here. And of course, what about for XC here? Of course, we have 50 over XC is 200. So 5 divided by 200 is going to be 1 over 4, or you can just say 0.25 amperes here. Okay, so these are the values of each one of these that is basically given or mentioned as we have there. So the next thing it says, find the value of the effective current of the circuit now. So how do you find the effective current of the circuit? So finding the effective current of the circuit is the same as finding the total current of the circuit. So finding the effective is easy enough. So let's just go ahead and do this one. Let's get this one back. So we have all the information that we need. So we can say I effective total, you can say it is IR squared plus IC minus IL, and then of course squared. You do the math, of course, or plug these numbers in. Of course, you'll be able to find the answer here. But this square should be here. Okay, and of course there's there. So we have 0.17. Let's not forget the square root. That is squared plus IC, which is 0.25 minus 0.08, and then the whole thing squared. You do the math, of course, you'll find the answer here, this much in amperes, let's say. That'll be the I effective. The next thing that we have says the value for the effective current, we have found this one here. So this is part A, we can say. That was part B, okay, and this is part C. Part D says, find the phase difference angle between the current and the potential difference of the source here. So, okay, now the last thing that we need to do is find the phase angle difference. For this one here, here's what we're going to do. Theta equals to, remember, so we'll say theta equal to tan inverse of course, since we have all of this, of course, we can say IC, don't forget, that is the rule, yeah, minus IL over IR. So everything you need, basically, for this equation you have. So tan IC, we have found IC, which was 0.25 minus IL, which is 0.08, and then, of course, divided by 0.17, that is IR. You do the math, of course, you'll find the answer. Let's just find the answer. That is tan inverse of 0.25 minus 0.08, and then divided by 0.17, and then now you can close bracket and press equal. The angle is going to be 45, and of course you can see that positive 45. What does it mean, positive 45? That means, remember, we said in parallel circuit, if the angle is positive, that means the current is leading the voltage by 45 degrees in here. Okay, so we can say the current leads by, the current is leading the voltage by 45 degrees. Now I don't have to say positive 45 again, because leading itself means positive, and that is basically how you can do it. Yeah, you can get it, of course, 44 by rounding, but of course you can get 45 altogether. And I would recommend you trying this one here. Of course, it's going to be very useful for you to see how these things are done, because sometimes the questions are pretty much the same thing. That is it for today. Next time, inshallah, we'll talk about the oscillating circuits, or basically the resonating circuits. When a circuit will be in a state of resonance, and of course when we have a circuit like this, or you can say when devices are connected in series, let's say. But that is all for later. So stay tuned, and of course we'll have more, inshallah. Till then, I'll see you soon. Assalamu alaikum.